So here we want to think about syn dihydroxylation from the perspective of synthesis, hopscotching from a reactant straight to a product. We just want to take into account the fact that these are going to be syn addition for the reasons that we discussed in the previous video, because of the shapes of this osmium tetroxide and potassium permanganate. The two oxygens that we add will add on the same side of the double bond. So you see an alkene, and you think, okay, we're doing addition reactions as opposed to substitution or elimination. Then you look at the recipe to see what you're adding. You see osmium tetroxide, so you know you're adding those two oxygens on there, and they're trying to be environmentally friendly here, or even just safe, by using as little osmium tetroxide as possible. That's what they mean by catalytic. And we saw how the structure of osmium changes over the course of the reaction. This NMO, the N-methylmorpholine N-oxide, that regenerates the osmium tetroxide. It takes the osmium that we saw that had two OHs on it, and it turns that back in to the osmium that just has the four O's, osmium tetroxide. So that's what that NMO is doing there. So you don't have to use a whole bunch of osmium. That is letting you just use the osmium tetroxide as a catalyst. Okay, so you see that recipe and you think, syn dihydroxylation. So you draw the carbon skeleton as it was, just without the pi bond. We're going to use that molecular glue to stick new things onto this molecule. And then you draw the two OHs, one on each of the carbons in the double bond. You want to make sure they're going in the same direction. So if one H is coming out at you, the other OH should also be coming out at you. Now we have chiral centers here. Both of those carbons with the OHs on them are chiral. And so there's no reason why one face of the double bond would be more reactive than the other. The pi bond is flat. These carbons in the pi bond are trigonal planar, so they're flat. So the reaction will happen equally on both sides, and if you have a chiral center, you'll form a racemic mixture of the two enantiomers. So to get the enantiomers, you switch the configuration of all of those stereochemical bonds. If a bond was coming out at you, you make it going away. If the bond was going away, you would make it coming out at you. So you'd get a 50-50 mixture of these two enantiomers. If you did syn dihydroxylation with osmium tetroxide on this alkene. Okay, now in this other reaction, they're not using osmium tetroxide as a catalyst. You're just using a whole bunch of osmium tetroxide, which is dangerous and toxic, and these reagents in the second step are replacing the osmium on the carbon chain with hydrogens to give you the diols. So you see your alkene, and instantly you're thinking, okay, we're doing addition reactions here, not substitution or elimination. What am I adding? You see osmium tetroxide, sodium bisulfite, and water. And you say, that's the recipe for syn dihydroxylation. So you would draw the carbon skeleton as it was in the reagent, but without the pi bond, and you would add two OHs on the two carbons that were attached, that had the double bond. Now, you want to draw these syn, both going in the same direction. And because we have a chiral center here, this carbon here is now chiral, we have to include both enantiomers. So to get the other enantiomer, you change the configuration of the bonds. If the bonds were coming out at you, then you make them going away. If they were going away, you'd make them coming out at you. And when you do syn dihydroxylation with osmium tetroxide on this particular alkene, you end up getting a 50-50 mixture of these two enantiomers. Okay, so in the next one, you'd see the alkene, and you'd say, okay, we're doing addition reactions here, not as opposed to substitution or elimination. We're doing addition because you know that that's what you do with those pi bonds. They're extramolecular glue that let you add things onto that molecule. And so you'd look at the recipe to see what you're adding. Now here we have that potassium permanganate. The transition metal with the four oxygens reminds us of osmium tetroxide. And then we're using sodium hydroxide and keeping it really cold in order to prevent unwanted side reactions here. So to get the product of this, you'd redraw the carbon skeleton. You'd see that recipe, you'd think, that's syn dihydroxylation. So you're going to add a hydroxyl group, an OH, on each of the carbons that were in the double bond. And the OHs will add on the same side, so they'll be syn, the same side of that pi bond. Now the carbons in that pi bond were trigonal planar, so this whole thing is flat, and the two hydroxyl groups could just as well add on the other side of the pi bond. So we'll draw the enantiomer here, where each of those hydroxyl groups added on the opposite side. So these two structures are enantiomers, and if you did this reaction, if you treated cyclohexene with potassium permanganate and cold sodium hydroxide, you would end up getting a 50-50 mixture, a racemic mixture of those two enantiomers. For D, you'd see an alkene, and instantly you'd be thinking, okay, we're doing addition reactions, as opposed to substitution or elimination. And then you would see that you have potassium permanganate, sodium hydroxide, and you're keeping it cold. That's a sign that you're doing syn dihydroxylation. So you would redraw the carbon skeleton, just without the pi bond, and on those two carbons that were in the double bond, you're going to be adding OHs. They're going to go in the same direction. They're going to add on the same side of that face. So you'd have OH for each of those. Now here you don't have any chiral centers, and so there is no need to draw the enantiomer. In the case of this oxygen on the right, that carbon has two hydrogens on it, so it's not bonded to four different things. And for this carbon in the middle, as if you go around the ring one way or go around it the other way, you run into the same things at the same distance. So that means that going around that ring in either way is the same, and so this is not bonded to four different things, and so it's not a chiral center. So that is the only structure you would get if you treated this alkene with potassium permanganate and cold sodium hydroxide. With E, you see an alkene, and instantly you're thinking that we're going to do an addition reaction, as opposed to substitution or elimination. To see what you're adding, you would look at the recipe. And the crucial thing here is the osmium tetroxide. You see osmium tetroxide, and you should instantly think, this is a very selective, very efficient way of doing syn dihydroxylation. It's just really toxic, so you don't want to, and environmentally unfriendly. So you don't want to use a lot of the osmium tetroxide. You'll just use a small catalytic amount, and as it gets used up, you'll regenerate it with this peroxide, as we talked about in the video on the concepts behind this reaction. So to draw the product, recognize this as syn dihydroxylation. To draw the product, you would redraw the carbon skeleton just without the pi bond, and on the two carbons that were in the double bond, you would add OHs, hydroxyl groups, making sure that those add on the same side. So either both coming out at you or both going away. And here, because this carbon on the left is a chiral center, we want to draw the enantiomer. So the same molecule, just with the OHs adding on the opposite side. Oops. And so these two are enantiomers. So you'd have a racemic mixture, a 50-50 mixture of those two enantiomers. If you did syn dihydroxylation with osmium tetroxide on this alkene. Okay, one more. We have an alkene. You see that and you should think, okay, we're doing addition as opposed to substitution or elimination. What are you adding? You look at the recipe. You see osmium tetroxide, so that you should think, okay, we're doing a very efficient but also very toxic and environmentally unfriendly syn dihydroxylation. So to do that responsibly, you don't want to just use this in stoichiometric amounts. You don't want to use that as your reagent. You'll use it as a catalyst. You add a tiny, tiny bit, and as it gets used up, you regenerate it with this NMO, that N-methylmorpholine N-oxide. And the N-methylmorpholine N-oxide regenerates the osmium tetroxide as it gets used up. Okay, so you'd recognize that as a recipe for syn dihydroxylation. So you can redraw the carbon skeleton as it was, just without the pi bond. And where the pi bond was, we're going to add, where the pi bond was, we're going to add 2 hydroxyl groups, one on each of the carbons that were in the double bond. We just have to make sure that they're syn. So if one is coming out, the other also has to be coming out toward us. Now we want to make sure that this looks appropriate for a tetrahedral atom. For a tetrahedral atom, you need 2 bonds in the plane, one coming out at you and one going away. So we have to make those methyl groups point away. That one pointing away, and this other one, because you have 2 bonds in the plane, actually one coming out, and you could have the hydrogen going away there, the implied hydrogen, so you don't have to change any bonds there. So we have chiral centers in that molecule. There's no reason why one face of this flat trigonal, of these flat trigonal planar atoms, this flat alkene, there's no reason why one side of it would be more reactive than another. So we're going to get a racemic mixture of the 2 enantiomers. To get the enantiomer, you switch all of the stereochemistry of the bond. So if you have a bond that's coming out, you make it go away. And if you have a bond that's coming out, you change it so it's going away. And if you have a bond that's going away, you change it so that it's coming out. So all the chiral centers switch. These 2 molecules are enantiomers. If you did syn dihydroxylation with a catalytic amount of osmium tetroxide on this alkene, you would end up with a 50-50 mixture of these two products. So hopefully that gives you a sense of how you can think through synthesis problems of syn dihydroxylation.